Good morning.
Good morning, doctor.
So we will start to do problems on chapter 15 to practice on the formulas we have covered together last time. So in a first problem, a 30 millimeter thick plate made of low carbon steel is to be reduced to 25 millimeter in one pass in a rolling operation. As the thickness is reduced, the plate width increased by 4%. The yield strength of the steel is given to be 174 megapascal, and the tensile strength is equal to 290 megapascal. The entrance speed of the plate is 77 meter per minute, and the roll radius is 300 millimeter, while the rotational speed is 45 revolution per minute. Determine the minimum required coefficient of friction that would make this rolling operation possible, and the exit velocity of the plate and forward slip. So here we are in a rolling problem, and we want to perform the operation in one pass. To be able to perform the operation in one pass through the rolls, this means that the draft of the operation should be equal to the reduction. So here we desire to reduce from 30 to 25. So the draft desired to perform per pass, if I want to just do one pass, I want to go from 30 to 25. So the draft is equal to 5 millimeters. Okay? I should calculate what should be the minimum coefficient of friction to achieve this operation in one pass. So I will say that I know that the maximum draft possible per operation is equal to mu square, which is coefficient, friction coefficient square, times the radius of the rolls. Okay. Now concerning units, we have that mu is without unit, and r should have the same unit of d. So here r is already provided in millimeter. The roll radius is 300 millimeter. So I can say that d is equal to mu square times 300. Okay. This equation will give me what is the value of mu required to perform the operation in just one pass. Then, what is the exit velocity of the plate? So whenever they ask for the exit velocity, think about the conservation of volumetric rate. Okay, we have seen together last time that the rate of material passing through the inlet is equal to the rate going through the outlet because it's a steady operation. So from conservation of volumetric rate, we can write that V0 times omega 0 times T0 equals to V final times omega final times T final. Now, concerning T0 and T final, they are provided. We know that T0 is 30, T final is 25. So this is T0, this is T final. Now, concerning the information about width variation, we have this sentence. We will use this sentence to convert it to an equation. As the thickness is reduced, the width of the plate is increased by 4%. This will give us a relation. So from this sentence, we can write that omega final is equal to omega 0 times 1 plus 4%, which is 0.04. So we can say that we can replace omega final by 1.04 omega 0. Okay? And concerning the velocity, they said that the entrance speed is given to be in meter per minute equals to 77 meter per minute. Just pay attention for units. So here, V0 and Vf should have the same unit, omega 0 and omega f also, and T0 and Tf also. So if you use in your equation V entrance in meter per minute, V final will be in meter per minute. Now, replacing in our equation here, we will replace V0 by its value, 77. In omega 0, we will leave it as it is because it will be simplified. And T0, we replace it by its value, which is 30, equals from the other side to V final, which unit will be in meter per minute, like V0, times omega final will be replaced to simplify omega 0. It will be replaced by 1.04 omega 0. And finally, T final will be replaced by 25. And always make sure to have same units for thickness in both sides. So here it's 30 millimeter, here it's 25 millimeters. So now, from this equation, I will simplify the omega 0. Omega 0 is unknown, but I don't need it because it will be simplified. So I will get the value of V final in meters per minute. This is the exit velocity of the plane. Now, they also are asking me for the forward slip, okay? By definition, what is the forward slip? The forward slip factor, S, is the ratio of V final minus V roll over V roll, okay? So to remind you of these formulas, we have seen them together here in the course material, okay? In the processes equation file, you have all equations starting from the definition in flat rolling, from the draft, the reduction, the conservation of volumetric flow rate here. You have, this is the forward slip ratio, it's a ratio, VF minus VR over VR. So just you should make sure to have the same units for VF and VR, okay? So now going back to the problem, to get the value of the forward slip, I need, V final is already calculated in part B, the exit velocity. I need to find VR. So I will see in my problem what is the information that can give me VR. You know that VR by definition is the linear speed of roll. Of course, when we the linear speed at the extreme point, yani at the farthest point from the center. So if this is your roll, okay, I will look at the linear speed of this point, which is just in contact with the work part. So I should multiply the angular velocity by the radius. So this is the radius of the roll, let's say. And at this point, I have the velocity tangent, okay, tangent to the circle, so it's perpendicular to radius, and VR is given by omega, which is the angular velocity. So let us call it omega r to not confuse with the thickness. Omega roll times radius. So let us see what they provided me. They gave me the radius of the roll and the rotational speed in revolution per minute. So make sure to do conversion of units. So in case you want here, for example, since V exit was calculated in meter per minute, I will also calculate, I want VR also to be in meter per minute. So to have VR in meter per minute, I should have the radius in meter, okay, the radius in meter, and I should have omega r in radians per minute. Now, to find omega r in radians per minute, since I know the rotational speed in revolution per minute, to convert to radian per minute, all I have to do is to multiply by 2 pi, because one revolution corresponds to a full rotation, 360 degrees, which is 2 pi radian. So here I can calculate then my linear velocity in meter per minute by doing 2 pi times n. Since n is in revolution per minute, when I multiply by 2 pi, I get omega in radian per minute. No need to convert to second because I need V in meter per minute. And I multiply by the radius and I make sure to convert to meter. So the radius is 300 millimeter. Then I multiply by 0.3 in meters to get my velocity in meter per minute. Once I have VR in meter per minute and VF is already in meter per minute, I can calculate the forward slip as V final minus VR over VR. Okay, so let us see together the details of the numerical solution. So to start with, I got the maximum draft is mu square over R. And since I know that the draft should be 5 millimeter, and I want to perform this draft in one pass, then the minimum coefficient of friction required will be 5 over the radius, and D in millimeter and R in millimeter. Millimeter will simplify. I get the value of my minimum friction coefficient. Now in part B, to get the exit velocity, we applied the volumetric volumetric rate conservation, and using the relation between omega f and omega 0 is simplified, and then I can get the value of V final. And since, as we said, V0 is in meter per minute, then I will get V final in meter per minute. And finally, we know that VR is 2 pi R times N, because 2 pi N is omega, and V is omega R. So I get my velocity in meter per minute. Then I replace in the forward slip relation, since the two velocities are in meter per minute. So meter per minute unit will simplify, and I will get S, which is a dimensionless number. So any question for this problem before we move to another one? Okay. A series of cold rolling operations are to be used to reduce the thickness of a metal plate from 50 millimeter to 20 millimeter in a reversing to high method. The roll diameter is 600 millimeter, and the coefficient of friction between rolls and work is equal to 0.50. The specification is that the draft is to be equal on each pass. So sometimes we might need several passes to accomplish a rolling operation. This is an example here. So we will determine first what is the minimum number of passes required, and then what is the draft of each pass. So first, from the given, we know the initial thickness. So this is T0. And we know the final thickness, which is T final equal to 20 millimeter. So you can from here calculate the total draft. So D total is the difference between T0 and TF. So it's T0 minus TF. It's 50 minus 20. It's equal to 30 millimeters. Okay. So this is the total draft. But this draft is very high, so it's not. I cannot easily find an operation that can do for me a 30 millimeter draft in one pass. So this is not usual. It's not a common value. So I need several passes in order to accomplish this operation. Now, in order to know how many number of passes is required, I will calculate what is the maximum draft that can be performed by this rolling operation. I know that the maximum draft per pass can be calculated as mu square times R, where mu represents the friction coefficient, okay, and R is the radius of my roll. Here mu is given, it's 0.15, so I have 0.15 square, and I pay attention to here. If I got already the draft in millimeters, so I will take the maximum draft per pass also in millimeter. So I will, since the diameter is 600 millimeters, then the radius is 300 in millimeter. So I get then the maximum draft per pass. So now, having the total draft and having the maximum draft that can be accomplished per pass, I can do the ratio to get the minimum number of passes. Okay, so now I can say that the minimum number of passes that are required to perform the rolling operation is equal to D total, to the total draft desired, over the maximum draft per pass, over D max per pass. Okay. Now pay attention that I should round this number, and if I obtain, for example here, if you perform the calculation, you will obtain that the maximum draft is 6.75 millimeter. And when dividing the total draft by Dmax per pass, you will get 4.44. Of course, you will not do half of a pass, yani you will do complete pass. So you will round up your number to the closest number. So then you get that it's rounded to 5 passes. So I need 5 passes to perform this operation. And since I will do drafts, passes of equal draft, so here I will tune my equipment in a way to have per draft, per pass, a draft of the total over 5. If you divide the total draft by the number of passes required, you get that you need to have 6 millimeter per pass, a draft of 6 millimeter per pass. Okay. Yes, we always round off, always, of course. Okay, so I cannot keep it with a number after the comma, so it should be a rounded number. Any other question on this? Another problem. A low carbon steel plate is 300 millimeter wide and 25 millimeters thick. It is reduced in one pass in a two-high rolling mill to a thickness of 20 millimeters. The roll radius is 600 millimeters and the roll speed is 30 meters per minute. The strength coefficient is given by 500 megapascal and the strain hardening exponent is given by 0.25. We want to determine the roll force, the roll torque, and the power required to perform this operation. So in this problem, I will remind you of the formulas that should be used. So here we want to calculate forces, torques, and power developed. So first, in the rolling operation, I can calculate the true strain. So it's like a squeezing or compression operation. So I do ln T initial over T final. This is the absolute value of epsilon. From this value, I can get the average flow stress, knowing the strengths, knowing the coefficient K and N. And once I find the average flow stress, I can calculate the force developed by the roll on the work part as the average flow stress times the area of contact, which is the width times the contact length. And the contact length can be predicted from radical of R times T0 minus T final. And for the torque, as we said last time, we consider that the force is acting at the middle of the contact area. So the torque is at a distance of 0.5 L from this point here. Okay. So the torque is 0.5 FL per roll. Pay attention. This is for one roll. So if you take the two rolls, the torque is F times L. And therefore, to find the power for the two rolls, I do the total torque, which is 2 times 0.5 FL, which is FL, times the angular velocity of the rolls, which is calculated as 2 pi n. So in total, I get that the total power required is 2 pi n times F times F. Okay, so we will apply these formulas in this problem, and we will consider variable radius to see what is the effect of radius on the force developed, the power developed, and the torque needed. So going back to the problem, first I need to find the roll force. So from definition, to get the roll force, I need to determine. So I have that the roll force F is equal to the average flow stress, Y average, times omega, which is the width of the plate, times L, which is the contact length. So I will start by computing what is the average flow stress. Okay, to calculate the average flow stress, I will use the formula, the following formula. The average flow stress is equal to K epsilon to the power n over n plus 1, where K is the strength coefficient and N is the strain hardening exponent. These two are given in this problem. So this is K. Strength coefficient is 500. So this is K. The strain hardening component is 0.25. So this is N. I just still need to get epsilon. Epsilon is the true strain. So I can just apply the formula that epsilon is ln of T0 over T final. And here both are given. So you have that the initial thickness is 25. So this is T0. And the final thickness is 20. So this is T final. So I will just replace in my formula to get that epsilon is a ln of 25 over 20. Once I obtain epsilon, I replace back into my formula. I replace K and N by their values. I can get then the value of the average flow stress. Now, for omega, omega is given. It's the width of the plate. It's 300 millimeter. So this is omega. Now, to calculate the contact length, we know that we have a formula for the contact length. The contact length is the radical of the radius times T0 minus T final. And here I can keep all dimensions in millimeter. Then what will happen if I keep all my dimensions in millimeter? I will get that omega times L unit is millimeter square. And what is the unit of the average flow stress? What is the unit of the average flow stress? The average flow stress is K epsilon N over N plus 1. Epsilon does not have unit. N does not have unit. So the unit of K is equal to the unit of the average flow stress. And since K is provided in megapascal, I will get that the average flow stress will be in megapascal. Now, if you multiply megapascal by millimeter square, what will be the unit of your force? Yes, very good. Newton. Why Newton? Because look, megapascal is 10 to the power 6 Pascal. Okay? And millimeter square is 10 to the power minus 6 meter square. So when you multiply megapascal by millimeter square, what will happen is that I have times 10 6 and times 10 minus 6, which will simplify. So megapascal times millimeter square is equivalent to Pascal times meter square. And Pascal times meter square is Newton, because by definition, SI unit in SI units, Pascal is Newton per meter square. So when I multiply Pascal by meter square, I get my force in Newton. So by replacing here, you will get your force in Newton. Once I find my force, the next step is to calculate the roll torque. When they say roll torque, it's the torque per roll, okay? And the torque per roll, by definition, is equal to 0.5 times the force calculated times L, which is the contact length, okay? Now, in case F is in Newton, if you keep L in millimeter, you will get your torque in Newton millimeter, okay? And if you want to provide it in Newton meter, then all you have to do is to multiply this result by 10 minus 3. Or from beginning, if you convert L to meter, then you get your torque in Newton meter. So it depends. Here you are free to do what you want since they didn't specify unit. If we specify the unit for you, then you should put the unit required, okay? Now, then they asked me for the power required to perform the operation. So now I want to calculate what is the power needed to, when they say power required for the operation, this means they want the total power, okay? And the total power, since I have two rolls, So to get the total power, I should do 2t times omega. Okay? So to get P now here, I need to do 2t, which is the torque I calculated in the previous step, times the angular velocity of each roll omega. Now here, what did they give me? They gave me the roll speed. So how can I get omega from the roll speed? What is the relation between omega and the roll speed VR? This is your roll, okay? We said that VR represents the linear velocity at this point, okay? So to get VR function of omega, I say that VR is equal to the radius of my roll times the angular velocity omega. Okay, so I can say then, so omega is the linear velocity VR over the radius. Okay, now since the roll speed is given in meter per minute, when you divide, so if I keep VR in meter per minute, and then I should divide by R in meters so that the meter unit cancel out, I will get then omega in radiant per minute. Okay, but in my equation, if I want to get the power in watt, which is the SI unit for power, if I want to get the power here in watt, what should be the units of T and omega? If I want power in watt, the torque should be provided in Newton meter. So here, if I already got it in Newton millimeter, I should do, to get it in Newton meter, I should multiply by 10 minus 3. Okay, and for omega, in this equation, I will get omega in radiant per minute. But here, to get P in watts, omega should be in radiant per second. So to convert from radiant per minute to radiant per second, the value obtained here, I should divide it by 60. Okay, so once I do this, I will get the power in watt. If you want, you can use this formula 2t omega, or you can use the formula developed in the course. So here, after replacing omega by its value, which is 2 pi, okay, they got that the power is 2 pi nfl. And to obtain P in watt, the n should be provided in revolution per second. Okay, so in this case, I can apply this formula 2 pi nfl in this problem, but I should make sure to have F in Newton, L in meter, and N in revolution per second. Okay, because if it is in revolution per minute, I should add to this equation over 60. Okay, I should add over 60. Okay, here they gave you, if you want, the units in SI and in English system. So if I am using English SI units, the power is in joule per second or watt, and the rotational speed should be in revolution per second. Okay. While if I work in English units, in case I want my power in inch lb per minute, then n should be in revolution per minute. Since we are working in SI system here, I will provide n in revolution per second. So here, just instead of 1, it should be revolution. هن قصدهم يعني 1 revolution per second. Okay, so here, if I go back to my problem, I can use the formula provided by the course material. Just I should make sure to have n in revolution per second. How to get n? N is omega over 2 pi. Okay, so all I have to do is to replace omega by v over r. I know that my velocity v roll is given, so omega, n will be VR over radius times 2 pi. Now for units, because I want n in revolution per second, okay, so I should convert my velocity, because my velocity, my VR is in meter per minute. So I should convert it to meter per second. So VR should be supplied in meter per second. So I should divide the value provided by 60. So here, when I divide by 60, I replace then VR by 0.5 in this formula. Okay, and the radius will be 600 millimeter. I convert it to meter, so it's 0.6. And over 2 pi to go from radian to revolution. Okay, so let us see the details of calculation here. So for the draft first, it's T0 minus T final. For the contact length, it's radical R times T minus T0 minus T final, which is the draft. I get the contact length. For the true strain, it is ln of 25 over 20. For the average flow stress, it's K epsilon n over n plus 1. For the rolling force, it's the average flow stress times the width times L. So I get my force in Newton. Then for my torque, if I want directly to obtain it in Newton meter, I should make sure to convert the contact length from millimeter to meters. This is why I multiplied here by 10 minus 3. And I use the flow stress in, I use the force value in Newton. So by multiplying in Newton and meter, I get that the torque per roll is 123.684 Newton meter. Then, in the final step, if I want to calculate the total power, if I want to use the formula of the course, which is 2 pi n times F times L, okay, I should use n in revolution per second. So this is why I converted n from, I used the formula for n anyway to have the final unit in revolution per second. So first what they did, they calculated in revolution per minute. They replaced VR by meter per minute, and they divided by 2 pi R, and R is in meter, 0.6. Because they didn't, they just replaced the velocity in meter per minute, they should convert back at the end from revolution per minute to revolution per second by dividing by 60. Okay? Or if from the first equation you replace directly by 0.5 the velocity in meter per second, then you will end up directly with the result in revolution per second. And once they got n in the unit specified, they replaced into the power equation, which is 2 pi n times F times L. And for units, they made sure to have n in revolution per second, the force in a Newton, and the length in meter, in a way to obtain at the end the power in watt. Okay, so here you obtain your power in watt, and if you convert to kilowatt, it's 206 kilowatt. Okay, any question on this problem? Okay, let us continue. Now, we will repeat the same procedure, but for different radius. Of course, we will not repeat the equations. We already know all equations. We will just together see what will happen if we change the radius while fixing the linear velocity of the roll, VR. So for the same, all values are fixed. I just vary the roll radius. And I want to see what will be its effect on the rolling force, the torque, and the power. Here we perform the calculation, but let us see together the analysis, what will happen when we increase the radius and we fix the value of VR. Okay, so first, to see the effect first on the force. What is the definition? If we go back to the definition of the force, okay, the force equation is F equal to the average flow stress, which will not vary here with the radius, of course. It's depending on the material. So since K and N are not varying and the initial and final thickness are not varying, so epsilon is the same, Y will not change. And the width also is the same plate, it will not change. What will change is L, which is the contact length between the work part and the plate. The contact length is defined as a radical R times T0 minus T final. So here, we are not changing T0 and T final, we are just changing R. So from this formula, we can see that F is proportional to radical R. So when R will increase, of course, F will increase. So we can expect that the rolling force will increase with increase of radius. Okay? And here in this figure, the blue curve represents the variation of the force with the radius. Okay? Now let us move to the effect on the torque. What is the torque equation? The torque equation is for each roll, the torque is 0.5 F times L. Okay? So if I replace now F by its value, I get that it's equal to 0.5 times the average flow stress, Y, average, times the width, which is not varying, times L times L. So I have L two times, one in F and one in, I multiply F by L, so I have L squared. So I can see here that the torque is proportional to L squared. So it's proportional to R, because if I replace L squared by its value, I get 0.5 times Y bar times omega, and instead of L squared, it's R times T0 minus Tf. So I can see that the relation between torque and radius is linear. So higher the radius, higher the torque. So the effect of the radius on the torque is higher than the effect of the radius on the force, since torque is proportional to R, while F is proportional to radical R. So here you can see that the torque is varying in a linear way with the radius, while F is proportional to radical R. So the slope of variation for the torque will be higher than the slope of variation for the force. So this curve represents the variation of torque with the radius. So until now, we deduced that both the force and the torque will increase with the radius. But what about the power? Concerning the power is torque times omega. Okay?